Hi everyone. In this video, what we're looking to do is to give you a brief introduction to the field of chemical kinetics. Or more specifically, how does the concentration of a product and a reactant of a reaction vary with respect to time? So rates are something that you've actually already had a decent amount of experience with, you just may not know it. So a classic everyday example that most of you have thought about, specifically those with on-campus jobs, is how much you get paid. And so the rate of pay of an on-campus job is $10 an hour. So we can actually then go ahead and put this in a mathematical equation, as you can see here, and that you can say that your rate of pay is $10 per hour. Oftentimes we express things in the denominator with this -1 exponent right here. Another really good example that you've probably seen previously is how fast you're driving your car. If you're going to drive the speed limit, which I hope most of you do, well, close to at least, you could say that the speed limit is 70 miles per hour on the highway. So for every hour, you're driving 70 miles. And so this is actually a rate of travel. Chemical reactions work really in the exact same way. So for example, the burning of methane produces 1 mole per liter of CO2 per second. And so we can then go ahead and write this mathematically that the rate of how fast we're producing this CO2 is in the units of moles per liter per second. And in this case, it would wind up being 1 mole per liter per second. And so an interesting thing about chemical reactions is that they don't have constant rates, and that they're going to depend upon the concentration of the reactants and products that you're building up in solution. And we'll talk about that in a little bit. Okay. First things I'd like us to think about is that the reaction rates do depend upon the stoichiometric coefficients that are present in the balanced equation. So for example, butane, which is just lighter fluid, when you burn that in oxygen, it's going to give CO2 and water according to this equation right here. So 2 molecules of butane react with 13 molecules or moles of oxygen gas, yielding 8 moles of CO2 and 10 moles of water. And so if our rate of butane concentration is decreasing at a rate of 0.20 moles per liter per second, how fast is the rate of water formation? Okay, and so what I'd like you to do is I'd like you to pause the video, see if you can figure this out. When you have an answer, play the video, and we will go through how to derive this equation quickly. Okay? Okay, and so in this case, what we're able to do is we're able to say that butane is being used up at a rate of 0.20 moles per liter per second. And so in the balanced equation, for every 2 moles of butane, right up here, that are being used, there are 10 moles of water, usually in the form of a gas when you're burning something like this, that are being formed. And so the rate of water formation is going to be 10 halves that of the rate of butane disappearance. And so in this case, what we wind up seeing is that 0.20 moles of butane times 10 halves, first of all, does not equal 0.2. So let's go ahead and fix that real quick. It's going to wind up being 0.5 moles of water per liter per second. And so we can see that this sort of makes sense. Because there are more moles of water being produced than the moles of butane being used up, we would expect the rate of water formation to be a little bit higher than the rate of butane being used up in this case. Okay. So the rate of reaction, so how fast these reactions are happening, are described by what are called rate laws. And so for example, if we take a very simplified reaction, A plus B yielding C plus D, we can describe a very generic rate law right here, in which the rate of the reaction equals a constant K, and this is something that has to be experimentally defined and is going to depend upon temperature and reaction conditions, times each of the concentration of the reactants raised to an exponent, either x or y. And so this is going to be the same for any different reaction that you're doing. Where this winds up varying is what the values of our exponents x and y are. And these exponents must be experimentally determined. It's super tempting simply to take our stoichiometric ratios here in front of a and b and use them as our exponents, sort of like we do with an equilibrium constant. In this case, this does not work. You have to perform an experiment to see the dependence of the concentration of A on the rate. And this exponent, this isn't necessarily always 1, but it typically is some sort of integer in most cases. So the exponents here are actually referred to as something called reaction order. So in this case, if our exponent x was 1, we would say that our rate of reaction is first order with respect to A. And all that means is that if we have the rate of reaction, if we double the concentration of A, okay, A raised to the first power, doubled, is going to double the rate of the reaction. On the other hand, let's say the exponent for B here, y, is 2. If we double the rate of the reaction, if we double the concentration of B, the rate of the reaction is going to increase more than double, simply because we have to raise B to an exponent power, in this case 2. So if we were to double the concentration of B with y as an exponent of 2, the rate of the reaction would quadruple. And in this case, with an exponent of 2, we would say that the reaction is second order with respect to B. The overall reaction order is simply the sum of all of your exponents in the reaction. So if x were to equal 1 and y were to equal 2, the overall order of the reaction would be 3. Okay, so how exactly are rate laws determined? And so, like I mentioned before, you've got to go ahead and determine this experimentally. And so what I've got is a very simple case here where you have isoprene, which is this diene here. Hopefully you guys can still name this. And this is going to dimerize to form a molecule called limonene. This is responsible for a nice citrus smell in lemons and limes. Okay, and so what I've done is I've shown you the initial concentration of isoprene in moles per liter. So it's either half molar or 1.5 molar. And then the rate of the formation of limonene that we've seen here. Okay, so to solve for this, our rate law is simply going to be rate equals our constant K, using the same type of formula we saw on the previous slide, times each of our reactants raised to a power, which we need to experimentally determine. In this case, we only have one reactant, isoprene, right here. And so we take the concentration of isoprene raised to some power, which is the order of our reaction with respect to isoprene, we'll call that X. So because we have some initial data here, we can solve for K and X using this experimental data. So for example, in this first column here, we can see that the rate of the reaction, 1.98, equals K, some constant that we would need to figure out, times the concentration, 0.5 molar to the xth power. Okay, and in the second row here, we have a higher rate, 17.8 molar per second, equals K, times our higher concentration, 1.5 molar, times that same exponent X. In both of these equations here, K and X are the same. And so two equations, two unknowns, we can algebraically solve for these things. So what I wind up doing is I wind up pulling the K to one side and everything else to the other side for both of these equations. Because K is equal in both equations, we can then set them equal to each other. And then with a little bit of algebraic rearrangement, we can solve for the fact that X equals 2. So in this case, our rate law for the formation of limonene from isoprene winds up equaling K, which is our rate constant, times the concentration of isoprene to the second power. And in this case, what this tells us is that the reaction order with respect to isoprene is second order. Because there's only one reactant, our specific reaction order with respect to isoprene is also our overall reaction order. And this is just a friendly reminder. You cannot directly take exponents from the stoichiometry of the reaction. Okay, let's give one more example. Okay, So this is a slightly more complex reaction here, where we're taking terp-butyl-bromide, reacting this with water to form terp-butanol and HBr. And this is an example of a reaction we're going to cover this week in lecture, known as an SN1 reaction. And so what I've done is I've documented the concentrations of terp-butyl-bromide, concentrations of water, and the initial rate of HBr formation. Keep in mind, the rate of HBr formation is going to be the same as the rate of terp-butanol formation, simply because our stoichiometric coefficients are the same. So using what we know for our template for the rate law, our rate is going to equal K, some rate constant, times the concentration of terp-butyl-bromide raised to some exponent, times the concentration of water to some exponent. And the reason I know to do this is, remember that your rate law takes this general formula where you have a term for each of your reactants. And in this case, our reactants are terp-butyl-bromide and water. Using the same strategy that we used before, see if you can figure out what our exponents x and y are. So why don't you pause the video here, and when you have an answer, resume the video and see if we got the same answer. Okay, so in this case, we know that our rate takes this general form, and what we can do is that while we can do this algebraically, it's actually a little easier to do this by looking at the data and asking ourselves a series of questions. Okay, when the concentration of water is constant, so for these first two rows here, we can make the assessment that, okay, this term is not changing. So our rate is going to simply be proportional with our rate constant put in there as well, to the concentration of terp-butyl-bromide raised to the x power. Because we're not changing the water concentration, it shouldn't really affect the change in rate. Okay, so because the rate doubles when the concentration of terp-butyl-bromide doubles, we can determine a direct proportionality. You double the concentration of terp-butyl-bromide, you double the rate. In other words, that exponent up here has to be 1. If it was any different than 1, let's say if it was 2, if you doubled the concentration of terp-butyl-bromide, the rate wouldn't simply double, it would quadruple. So in this case, x is going to be 1. We do the same type of analysis then when we hold terp-butyl-bromide constant. So for example, this first row and this second row here have the exact same concentration of terp-butyl-bromide, half molar concentration. And what we do is we double the concentration of water from 10 molar to 20. And in this case, we can then make the assessment that the rate of this reaction is going to be really proportional to the concentration of water raised to the x power. And this is also because really our concentration of terp-butyl-bromide isn't changing, so any change has to simply be from the concentration of water. But what you can see is that even though we've doubled the concentration of water, the initial rate of formation of HBr, which is our product here, doesn't change at all. And so this means that our rate up here doesn't depend at all upon the concentration of water. The only way that we can make this wind up happening is that if we make our exponent y equal to 0. Because remember, anything raised to the 0th power winds up equaling 1. And then at that point, K times terp-butyl-bromide times 1 is just K times terp-butyl-bromide. The concentration of water won't matter. Okay, so we take this information, plug this back into our rate law. Rate equals K, a constant, which all rate laws will have, times the concentration of both of our reactants, in this case, terp-butyl-bromide and water, raised to our exponent powers. In the case of terp-butyl-bromide, 1, and in the case of water, 0. This then simplifies down to a reaction rate of K times the concentration of terp-butyl-bromide. Cool. Just a friendly reminder, you can't take our exponents here directly from our stoichiometric ratios, otherwise water would be to the first power, which it's not. And the cool thing is in the upcoming classes, we're going to determine that the exponents which are describing this reaction order can actually give us some pretty cool insight into what type of reaction mechanism is actually taking place. Hopefully this helps, and I'll see you in a couple of days in class.